Good afternoon. It's my great pleasure to welcome Professor N.D. Haridas to deliver a special colloquium at the Raman Research Institute. Actually, I should say I'm happy to welcome him back to our Raman Research Institute. He was at Raman Research Institute from 1976 to 1980. In the very early years. After he had worked at University of California, Los Angeles, and then he had done a PhD at University of California, Santa Barbara, Masters and BSc in Delhi. And going on, he was at Niels Bohr Institute, NICAF, and then the period that I probably know him is he was at Math Science, IMSC. There, of course, his expertise is in the area of gravitation, field theory, and high energy physics. He has been very effective in conveying what he knows to younger generations. So he's been very interested in teaching. Another point of contact, if Professor Haridas remembers, that I went to see Kabru, which was 2004. Was a few years since I'd come to IUCAA, and I was building a HPC there because IUCAA I thought should have a HPC, and then I was told the fanciest HPC is in math science, so I went to see that. I'm not so sure, but you had already retired soon after that, maybe 2005 or something. Okay, great. So he has authored books, The Essentials of Thermodynamics, and the second book, From Strings to Strings, has been released by Springer as lecture notes in physics. He retired from math science, but also as a DAE Rajaramana professor at ISC and adjunct professor at Chennai Mathematical Institute, and had a visiting professorship at TIFA Hyderabad. So, I'm really delighted that we could have him, and it was quite a chance thing because he has come here to research on some article that he's writing, and I'm also happy to note that he pointed out RRI library being the ideal resource place where you can find what you want, and so it was a delight that he could spend time and give us this talk. So without further ado, let me invite Professor Haridas for his lecture. Please.
Thank you, Tarun, for your very gracious introduction. It gives me great pleasure to be back in RRI and this auditorium. In fact, almost 50 years ago, I gave my first talk here on the binary pulsar, the gravitational spin precision, which developed following my first visit to RRI and a lot of discussions with Radhakrishnan. Before I go on, I would like to make one apology, and that is my hearing aid broke this morning. Therefore, I may have difficulty hearing what you say, so you must help me with that. If you have questions, maybe you can just write it in a small piece of paper, and I will try to answer that. I must tell you a little bit about how my first visit to RRI came about. I did an extraordinary road trip in '74 from Munich, where I was working in the Max Planck Institute, to India. And Ramnath Kaushik, whom many of you know, it was his car, and we drove here. And this was November 74. And shortly before that, somewhere in October, Max Planck Institute at the time, the top was theoretical physics, where Heisenberg was still alive and he would come once a week, and the ground floor was astrophysics, and we used to often meet, attend each other's seminars and so on. And Freeman Dyson made a visit for one whole year at that time, and he would bring many people together, and he made an announcement about the binary pulsar, which was discovered by Hulsey and Taylor, and there was a lot of excitement about it. And to me, this was very significant because I must recount briefly my own experiments with gravitation, not experimental gravitation, experiments in trying to understand gravitation. So when I was an honor student, I tried to read Einstein's ABC of relativity, and it was good reading, but I didn't understand anything. In fact, Bertrand Russell's little book somehow made more sense. Nothing much happened. Then I went to Santa Barbara in 67, and I took a graduate course on general theory of relativity. This was taught by Harold Lewis, who was Oppenheimer's law student. And in fact, even in the movie Oppenheimer, there's a brief mention to him. And this course was full of G mu nu, Christoffel symbol, Riemann tensor, etc., etc. And even though I got an A, the physical content of the theory was still very obscure. So at the end of the quarter, Lewis asked me, how did you like it? I said, Hal, I still don't understand how the apple falls. This is all full of formalism, but couldn't relate it to any phenomenon. Then I did an independent study with Jim Hartle, and that was on singularity theorems, full of mathematics. So nothing much happened. Then I went to UCLA as a postdoc, and around the time, Julian Schwinger had his own approach to all of physics, including gravitation. And I found that very appealing. And Weinberg brought out a book on cosmology and gravitation, which left a deep impression because he was talking the language which we particle physicists could relate to. And suddenly, my understanding of gravitation increased leaps and bounds. And one of the tests of general relativity, which was still unrealized, was the Stanford gyroscope experiment. This was spearheaded by Schiff, the guy who wrote the quantum mechanics book. And I was always thinking about it. So when Dyson said there is a binary pulsar, it immediately occurred to me, the pulsar being the most stable clock should be the ideal way to check this gravitational spin precision. So I made some very rudimentary calculations and showed it to Dyson, and he said, this is very good, but at this stage you should go a little bit beyond circular orbits, because at the time that was all I could do. And then he told me, since you're going to India, you should explore whether the Ooty telescope is willing to spend time observing it, because he, according to him, the Ooty telescope had many advantages. So I thought I will come to RRI and talk to Radhakrishnan, and that's how it started. I was visiting CTS at that time, and then he told me about the Radhakrishnan Cook model of pulsars, and we figured out that one of the good ways of detecting this pulsar in the binary is to look at pulse profile modulation and the polarization sweep. So I worked it out in his theory, and we wrote a paper on the new binary pulsar and gravitational spin precision. That was the first paper of mine from RRI, and the talk here was also on that. But as soon as I went back to Munich, a lacuna became very clear. All the relativity books and the Stanford experiment, they were worked out for a case where the gyroscope was much, much lighter than the gravitating object. But in the binary pulsar, that was not true, because both of them were equally massive. And I started thinking about it, and the paper that gave an answer, which is still being quoted, was a very strange calculation of two spin-half Dirac particles interacting through gravitational one-graviton exchange, and then they worked out what the spin dynamics should be in the classical limit. Now, this seemed very strange. Why Dirac equation of elementary particles should have anything to do with this manifestly classical problem? And classical limit is very tricky, because you take h bar to 0, but the spin angular momentum of the Dirac particle is h bar. So if you're not very careful, you'll be throwing away many spin-dependent interactions. So with my Chinese collaborator, we started looking at it from Schwinger's source theory point of view, and we found the correct formula when the two masses are comparable, and that agreed with this quantum calculation, and I'll come back to that later. And so, in some sense, the first classical derivation of this gravitational spin precision in binary systems was due to us. Even general relativists had problems calculating it, and people like Ehlers and Borner, they were all in the same institute, so they were also working on it. And 3 months later, they derived the general relativistic treatment, which was quite complex, because in GR you have to worry about what is observable. You can write down equations, but what does a distant observer observe? This is a very tricky problem. And so that is how the interaction with RRI and my serious involvement with gravitation, followed. So now I'm going to describe to you work which was done a few years after I joined RRI. I joined RRI in 76, and in 79 I started looking at gravitational radiation. I'll tell you why I started looking at it. This was at a time when hardly anybody in India, including at RRI, was thinking about gravitational radiation. Today, it's fantastic. We have, present here people who contributed greatly to the success of gravitational wave detection, and it all seems magical that within a span of less than 10 years, that whole thing has developed so much that one can now seriously and without feeling immodest talk about gravitational wave astronomy. And very soon, India is going to have its own gravitational wave facility, and under leadership of people like Tarun, we are in for very exciting times. So gravitational waves, from my times to here, has been a big, big journey, and I'm very fortunate. We are all very fortunate to be living in those eras where, truly scientific revolutions take place, and that is the ultimate reward for us. So I will describe to you what motivated me to look at the gravitational radiation problem, and what is it that we did, and maybe with some comments on future. So this is the background. Cho is my collaborator, and we worked out this gravitational spin precision. And the GR derivation was given by Jürgen Ehlers, very, very famous general relativist, somewhat later. Ours got published in '76. That's because Annals of Physics takes a long time to accept manuscripts. And I also told you about this quantum calculation and my work with Radhakrishnan. So the idea was to look at pulse profile and polarization sweep. Today, you hear stories about how black hole spins have been determined through the spin precision effect. And binary pulsar also already in 2005, they had seen it. But unfortunately, our work hardly gets much citation, but that is a professional hazard. It is disappointing, but one should not worry too much about it. Point is, whatever we did was right, and that's the real reward. So, now we are in year 1976, by which time the monumental amount of papers on gravitational radiation, all kinds of studies had been done. Chandrasekhar with his student Esposito had worked out, beyond the leading order, that is Einstein quadrupole formula, etc. And beautiful work about various conserved quantities in a binary system. When in a binary system and there's gravitational radiation, there's energy loss, but still angular momentum loss. But a combination of these losses is conserved, okay? Things like that. Some very, very nice results. But 76, Ehlers, Rosenblum, Arnold Rosenblum, my friend who visited this place, unfortunately had a very tragic end, but that's a different story. Goldberg and Peter Havas, they wrote a paper and they criticized not only Einstein's derivation, but all the previous derivations also. And they brought out several subtleties that they said must be looked into before we can trust this quadrupole formula. So it turns out that Einstein was clumsy in his derivations, but his final answer was right. And Landau and Lifshitz to some extent explained why Einstein got the right answer even though he was clumsy. And it turns out that Landau and Lifshitz also had been clumsy at a somewhat higher order than Einstein's clumsiness, etc., etc. These are, things that students should learn, that even masters can be clumsy. And in particle physics, we know people who write papers where a lot of clumsiness in the derivation, very deep ideas, correct answer. Maybe there is some sixth sense which tells them what the correct answer is, okay? But we cannot afford to have this clumsiness, because that really cast a doubt on the result. And that's what Ehlers and others were pointing out, that all these derivations should be re-examined. So what did they say? The light cones in the presence of a gravitating body, if you go very far away from the gravitating body, you think that space has become almost flat, and the light cone should be that of a flat space-time. This is not quite true. There is a logarithmic effect with respect to the light cone, And ALS and others said issues like this should be carefully investigated. So this is radiation zone. Many people like Chandrasekhar sister had pointed out how in the near zone you have to be very, very careful of the gravitational radiation. That is not at all surprising. If you do electromagnetic radiation, near zone calculations are full of subtleties, so you have to be very careful. 78, Rosenblum produced some 1,000 pages of calculation. He brought all of them here. I still remember we used to have an office upstairs. They had on a big table, Vishu and Chitra, who was a postdoc. They had these xeroxes of these 1,000 pages of Arnold Rosenblum going through page by page. Arnold Rosenblum claimed that you really need third order post-Newtonian calculation to get even the leading order, so-called leading order result correct. Sounds very counterintuitive, but in gravitation, anything can happen. Not only that, he claimed that the actual result is 2.5 times that predicted by Einstein. Now, 2.5 times is a huge effect. But at that time, there was no direct or even indirect determination of what the energy loss from a binary system should be. So Arnold Rosenblum came here, and he was already my friend from Munich. And this is what triggered my interest in this problem. And buoyed by the success of using Schwinger's source theory to the gravitational spin precision problem, I thought I'll take a look at the gravitational radiation problem also within Schwinger's source theory. It is possible, but it turns out that you have to be very, very careful. So I was wondering, is there some other way of approaching this where you don't have to do this tightrope walk? And that's what I would like to describe today. Of course, postscript, Einstein's quadrupole formula agreed beautifully when the binary pulsar data piled up, and in 1982 the orbital decay could be plotted, and I'll show you that graph later on. It's an impressive agreement. So experimentally, no doubt that the quadrupole formula was right. The theory was messy. Sorry. So I approached it inspired by Weinberg from the point of view of spin-2 theories of gravitation. So in particle physics, we believe that every representation of the Lorentz group should have a role to play in nature, and the massless spin-2, actually helicity-2, representations of the Lorentz group, when exchanged, give rise to gravitation, and they reproduce all the results of GR. Now, this is a fantastic connect between two different worlds. So I understood quantum field theory. I thought I will use this method instead of Schwinger's source theory method. So we set up a Feynman graph calculation. So you take a Lagrangian, which comes from the Einstein-Hilbert action, and look at fluctuations around flat spacetime. And for the fluctuating part, you write down all the interaction terms, Feynman diagrams can be generated, and use them to calculate whatever you want, almost whatever you want. This work was done with Vikram Soni, who is unfortunately now very ill. So it's my way of remembering the old times to be talking about this joint work. You may say, why go to quantum mechanics to understand something which is purely classical? It's a perfectly reasonable question. Wherever I gave this seminar, they say, why do you want to do quantum field theory? This is a classical problem. Correct. But there is nothing wrong with that. If the underlying world is quantum mechanical, you may be perverse enough to calculate how the apple falls by looking at quantum field theory. Nothing wrong with it, but it's a very tortuous route. Philosophically, you may say, well, the world is quantum mechanical, that's the way you should really do it. But our motivation was not philosophy. I'm not a fan of philosophy, okay? And I think philosophers have obscured more than clarified issues that are helpful to us. And I like to quote Leibniz, who said that, who is supposed to have said that. Philosophers kick up a lot of dust and then complain that they can't see clearly, okay? So, philosophical motivation. But this criticism, so classical general relativistic approaches were under a shadow of doubt. And therefore, I thought an independent way of doing this would be looking at quantum field theory and see what I get. What are the obvious advantages of the Feynman graph method? Energy momentum conservation at each vertex automatically guarantees the equations of motion. Even such a thing as radiation reaction is in some sense buried in all these conservation laws at each of these vertices. And since we eventually want to look at a classical problem, you don't have to worry about the non-renormalizability of gravitation, which arises only at the level of loop diagrams. So only tree diagrams are sufficient to get this result. So these were all very encouraging aspects. Oh, I keep flipping the wrong. Yeah. Now, general coordinate invariance of GR, by the way, there's a lot of misunderstanding about what general coordinate invariance really means. It is not a symmetry of GR. Any theory can be made general coordinate invariant, even Newton's law. It is just like properties of a triangle don't depend upon which coordinate you choose. As simple as that. Einstein himself was confused about it till a German mathematician pointed out that general invariance by itself is empty of physical content. It is it gives you a very powerful grip. But in spin 2 approach, this becomes gauge invariance, which we know has content. Okay. Of course, many objections to the spin 2 theory have been raised. And first of all, in the beginning, people would say, how would a black hole come out of a spin 2 theory? Now we understand how it comes about in a very difficult way, but it does come about. In fact, you can ask, can I get a hydrogen atom from quantum electrodynamics? Again, the path is very, very tortuous. Okay? You have to sum an infinite class of diagrams in QED to get a bound state. So bound state problems in quantum field theory are always problematic. But let's put those issues aside. One of the most serious objections to doing this is that no credible quantum theory of gravity is available in the market. Even 45 years after this work, we still don't even agree on what quantum gravity is. Okay? So these are some valid issues, but it turns out that because you are ultimately interested only in the classical limit, many of these problems facing construction of quantum gravity don't matter. And that's the point. Tree graphs of Feynman theory, not even loops, are enough to capture the problem. But I would like to mention that if you don't insist on renormalization, but simply regularize the quantum gravity theory, that means you provide a regulator so that all answers are finite, and that formalism exists, and it is as rigorous as regularized QED. But eventually you want to remove these regulators, and that's where all the problems of quantum gravity come. And another advantage is, even if you look at the Landau-Lifshitz derivation or Einstein's derivation, that to make use of what is called a pseudo-tensor, gravitational pseudo-tensor. It is pseudo, and everything pseudo is problematic, whether it is pseudo-science or pseudo-energy momentum tensor. The Feynman graph method avoids these difficulties. So these are some technical advantages. One of the serious issues when you do a Feynman graph calculation is what are the small parameters of the theory? Because you want to do a perturbation theory. Just as in QED, you have the fine structure constant. This is usually taken to be Gm over R. And for most astrophysical objects, leaving black holes, this is a small number. Even for fairly compact neutron stars, this is only about a tenth. Okay? So it's a small number. But when you set up the Feynman graph method, potentially Gm1, M2 is a dimensionless parameter. And this is huge if you take M1 and M2 to be those corresponding to astrophysical objects. So now you have to understand why such a large parameter doesn't come and screw up perturbation theory in the Feynman graph approach. And this is a very, very subtle problem. Full resolution, we don't understand it. And in QED also there is a similar problem. And this is called the infrared problem. If you take any process, scattering process, you can consider processes where photons are radiated with very, very low energy. And you add up all these 1 photon, 2 photon, etc. And that leads to infrared modification of QED. QED is a simple theory, so we can understand it. But in gravity, this is quite problematic. In fact, in its complexity, the infrared problem of gravitation is very close to the infrared problem in quantum chromodynamics. In fact, the whole quark confinement could only be understood after the infrared problem of QCD had been understood. Now in QED, for example, even in our BSc honors we did this Coulomb scattering of electron-proton. You can set down the Schrodinger equation, solve it exactly, and this infrared problem exchange, 2 photon exchange, etc., to get this infrared behavior correct. And what does it do? Far away from the proton, the electron wave function is not a plane wave. It is what is called a Coulomb distorted plane wave, where the phase grows logarithmically with distance. We will see the importance of this for gravitation in just a moment. It turns out that is exactly the exact analog of the logarithmic distortion of light cones in gravity. So you set up the Feynman diagrams, and here is the scattering, and the wavy line is the graviton, and graviton can be emitted from external lines. The exchange one can be graviton or electromagnetism. Because of the nonlinearity of gravitational theory, you pick up self-interaction and vortices where there are two gravitons, etc. Just look at it for 5-10 seconds. If you have never done a Feynman graph calculation, doesn't matter. Pictorially imagine that this is the amplitude for emitting a graviton during the collision process. And you can classically interpret this as radiation of gravitational, emission of gravitational radiation during scattering process. So you go and challenge the calculus. The exchange particle need not be graviton. It could be photon. So during the electromagnetic scattering, what is the amplitude to emit gravitational radiation? It turns out that Einstein's clumsiness didn't matter for this at all. But his clumsiness mattered a lot when the scattering itself was gravitational. So there are a lot of details. Details are important, but not to understand. Some people say the devil is in the details. People like Dyson would say God is in the details. Depend upon your theological, attitude. Details, whether God or devil, are important. But for understanding, you can put it aside for a moment. So this is the answer you get. Quite a simple answer. Q is the momentum transfer, and mu is the reduced mass. And you do the same thing for electromagnetism, and you notice something wonderful. That apart from numerical factors, the amplitude for emitting gravitational radiation, when the scattering is gravitational versus when it is electromagnetic, they are the same. And that is that factor there. So this is that in the curly bracket is exactly the same. So this shows there's a universality for the emission of gravitational radiation. There's one more curiosity. If you look at quadrupole radiation in electromagnetism you can have dipole radiation, quadrupole, octupole. The quadrupole radiation in electromagnetism is of the identical form as the quadrupole radiation in gravitational, except for a numerical factor which changes from E squared to something that depends on masses. So that's why it's good to look at gravitational radiation problem from various perspectives, because you see a beautiful universality. Today, if you look up Schwinger's classical electrodynamics book, he gives you an elegant derivation of quadrupole radiation in just one page, not 1,000 pages of Arnold Rosenblum. My friend Ravi Prakash Rao, who was here and was in Chicago, told me how Esposito and Chandrasekhar, their calculation was 600 pages. Okay? Our calculation was a dozen pages. Okay? Far from 600 or 1,000, but not as good as one page of Schwinger. So we are continually improving our understanding of the quadrupole formula. From the physics point of view, this is very important. Now what happens? Far away, it's not plane wave. Even the graviton wave function is not a plane wave. and you must put this into account. And that's complicated. It's in our paper, and when you do that, you have to, you get factors like this. Okay? Nu is Gm1, M2. The big parameter comes here, but notice that it always comes with I nu. So if you look at the probability in quantum theory, the dependence on this large parameter disappears. It's a miracle. Same thing happens with Rutherford scattering in QED. If you do the infrared, there is such a factor, but when you look at the cross-section for Rutherford scattering is the same as what you would get from classical Coulomb scattering. Okay. So now let's look at the gravitational wave function in the radiation zone. Radiation zone is where the distance is very large, and you get it like that. Now notice that you can define a new time variable and recast it as I omega t star. And this new time variable is precisely the one which Anderson used. Anderson, not of condensed matter, but Anderson of general relativity, to describe this, distortion of light cones. So the Feynman approach gives it naturally. And as I already told you, it doesn't affect not matrix elements, but probabilities. So the final result for the amplitude between an initial state and a final state with a graviton emission takes a very simple form, where you see the familiar third derivative of the quadrupole tensor. Okay? And this is what I call a one graviton transition operator. In general relativity, this is sometimes called the source, effective source, which in the Newtonian approximation is just a quadrupole, but as you go to higher and higher ones, you have to consider corrections to do that. Now let's do the electromagnetic radiation. Same way, you find that instead of the third derivative of the quadrupole, you get the second derivative of the dipole. And that is well understood dipole radiation, beautifully explained in Jackson. And what is the power radiated? It is square of the second derivative of the dipole. So immediately you can say the power radiated in the gravitational case is the square of the third derivative of the quadrupole tensor. There's one conceptual jump here, and that is in quantum mechanics these are operators, but when you go to classical limit, use Bohr's correspondence principle. That what was an operator, you now evaluate them on classical trajectory. That's all. And then the Einstein quadrupole formula emerges. Okay? So in this way, Einstein quadrupole formula gets derived the same way as a Larmor power formula in classical electrodynamics. This work was finished in '79, and it took 3 years before it could be published, because the general relativistic referee didn't understand the field theory part, and the field theory referee didn't understand the gravitational part, and we suffered from both camps. And I was about to give up, then one very enlightened referee, I won't name him, he saw the virtue of our approach and agreed to publish. It took 3 years for that. So when the paper got published was around '82, and that's the first time an experimental evidence for gravitational radiation came from the binary pulsar. It is indirect, because if gravitational radiation is coming out of the binary pulsar, the energy of the system keeps going down, and the orbit keeps shrinking. So the orbital decay could be very accurately monitored through pulsar timing. Today, pulsar timing has become, an art. Okay. And they fitted the orbital decay to what you would get from Einstein's quadrupole formula. And this is till 2005, but look up to 82, already there, it was amazing agreement between the quadrupole formula and the orbital decay. And experimentally, we no longer had any doubts, and theoretically, we didn't have any doubts either, and that's the story of the quadrupole formula. And now this has become more and more accurate. How much time do you have? Can I take 10, 15 minutes? Yeah. Now I'll describe a second route which I followed, which is really for us particle physicists a magical formulation. Without knowing anything about a theory, you can draw a lot of conclusions about its experimental consequence. So how is it possible? It's possible. You can't get all the answers, but you get some, and even getting the sum is already fantastic. And these are called low energy theorems. So there are certain theorems which hold when some of the energies involved are low. You may ask, what do you mean by low? You have to scale up the problem, etc. In our interview, they would say, what is Planck's constant? And we never remembered it, and we would say, sir, it's very small. Then they would keep persisting, how small? And you either gave up or you mumbled something which was hopefully wrong, but sometimes you got it right. So I will tell you about the magic of these low energy theorems. And I applied the low energy theorems to the gravitational radiation problem, which is quite involved, and derived the Einstein quadrupole formula. This work is still unpublished because I had the same issue. After struggling with particle physics, Weltman, who got the Nobel Prize for proving the renormalizability of Young-Mills theory, was the editor, and he told me, look, I completely sympathize with you. With all my works on gravitation have the same problem, so you must go to some other journal, go away from either journals of gravitation or of particle physics. Finally, it ended up with somebody who was a dogged referee, dog of a referee maybe, but I love dogs, so I should not say that. And he really refused to let this paper go anywhere, and I got tired of it and I left it. Those days there was no preprint system, so I don't have a preprint evidence for this, but in the Bohr archives, this paper is still there. Much later, Pasha Kabir, he was a very famous particle physicist of Indian origin, and he told me, the guy who was giving you so much problem was your next door neighbor in Niels Bohr Institute. So a wall separated him from me, but I didn't know that. He happened to be the last student of Niels Bohr. So in my scientific life, I keep bumping into these last student of Oppenheimer, last student of Heisenberg, last student of Niels Bohr, and sometimes I think I understand why they were the last students. And in my case, the very first student was also the last student. They are very powerful techniques, and these were pioneered by particle physicists when they didn't know what the theory of strong interactions was. And still they wanted to understand various properties of strong interactions. So this was pioneered by Nambu, Schwinger, Weinberg, Mandelstam, many others. Earliest example of this was Francis Lowe. Low energy theorem is one law, but this is Francis Lowe. His name itself was Lowe. And he showed that you could understand Compton scattering of photons and protons when you had no idea what the structure of the proton was. The structure of the proton was determined by QCD. And he showed if the photon frequency is very low, then this is given by charge, magnetic moment, etc. And this he could show it in quantum field theory. So structural details were irrelevant. He also showed that power radiated through electromagnetic radiation was entirely determined by the time derivative of the dipole moment. It is in fact this that I use to analyze the gravitational radiation problem. It turns out the Lowe's theorem actually gives more, and now I realize that what I did for quadrupole radiation, it actually gives octupole radiation and all that for gravitational radiation. So let me give you a little example of the power of low energy theorems. This is due to Weinberg. So consider a scattering process, very general, set of particles incoming, going into set of particles outgoing. Now you ask, what is the amplitude for emitting one extra photon when the photon frequency is very low? But you have to apply gauge invariance because all electrodynamic processes have to obey gauge invariance. And you apply gauge invariance, you get the condition that the sum of the charges of the initial particles is equal to sum of the charges final. But that's charge conservation. Not surprising. But when you do the same thing for gravitation, if kappa is the gravitational coupling constant, two are compatible only if kappa I is the same for all particles, including gravitons. And this is nothing but the equivalence principle, that the gravitational charge is universal. It's actually ratio of the gravitation to inertial mass. That's what this kappa is. So principle of equivalence emerges automatically from the low energy theorems. Then I've already given you this background about the Hulse-Taylor pulsar, and we applied the gravitational analog of low energy theorems first, and we obtained for the energy momentum tensor a universal result like that. It didn't matter what the internal constituents or the fields that went into this energy momentum tensor. The matrix element is completely universal. And it turns out that this single low energy theorem result accounted for all the classical predictions of GR, including light bending and everything, except perihelion shift and gravitational radiation. So there is a technology for how to do it. Since time is running out, I'll very briefly describe it. You start with so-called S matrices, and when radiation is very soft, you look at all the diagrams, and you find that when the graviton is emitted from the external legs, that sum is not gauge invariant. So you have to make it gravitational gauge invariant, you must add what is called inner bremsstrahlung. So here is a scattering matrix. There's scattering and there's graviton vortex, a lot of algebra, forget about it. So the graviton can come from the external legs, But if you add it, it's not gauge invariant, and you must add a graviton coming from the blob and put everything together. Okay? So we will avoid all this formula and tell you what the final result is. And like in GR, you work out in some gauge condition, transverse gauge, transverse traceless gauge, and so on. So for electromagnetism, if you do this, you get, that's the electromagnetic scattering, you get the dipole term and a quadrupole term. And for gravitation, you get the same quadrupole term. And electromagnetism, dipole is leading, electric quadrupole next. So these are V over C corrections. So in gravitational case, leading is quadrupole, next is octupole. Now again some technicality, I'll skip this also. What are the results? When I put together, I got the same one graviton transition operator as I got from the Feynman graph case, which we had already showed gives the correct Einstein quadrupole formula. Then there is some standard model low energy theorems, which I'm going to skip. So now, as I already pointed out, I should be able to get the octupole radiation also by this low energy theorem. The so-called gravi-magnetic quadrupole part can also be obtained. Now, this is all done in flat space. What happens if you're looking at gravitational radiation in, non-trivial spacetimes? This is quite a difficult problem, and you can make sense only if those spacetimes are at least asymptotically flat. Otherwise, it's too complicated. So now there has been a lot of interest in these so-called super translations, soft graviton theorems. Strominger, Casaccio started it, Ashok Sen and Ladda have also reanalyzed this. The main difference between Ashok Sen, Ladda's analysis and mine is that mine was all based on space-time description. They do it in momentum space, but obviously these are all related, and I want to explore. This is what I said 5 years ago. So you see, as I'm getting older, it is not easy to make progress, and I'm a one-man army with distractions from my cat and dog. So, but I'm not competing for anything. So if I do this, fine. If I don't do it also, it's fine. And I hope at least I've conveyed to you how you can use non-GR methods to not only qualitatively, but even quantitatively understand gravitational radiation. Thank you. I'll be happy to answer questions, but I already told you that I have a receiver problem.
So are there any questions? Okay, Ajit. I'll repeat it close to him, or you can.
So the last, it's very amazing to hear your this history. It's amazing to hear this history. Thank you for this talk. So the last 2 decades, there is a lot of work in using these effective field theory methods to compute higher order post-Newtonian calculations. Are they different from your approach, or?
Essentially. In fact, when the early effective field theory approaches came, I had to referee some of these things. In fact, the low energy theorems can either be done this way or through Lagrangians, which capture the essence of the low energy theorems, and those are called effective Lagrangians. Okay? But now the only problem is, sometimes people become more royal than the king. So they are pushing effective field theories so much in the direction of fundamental field theories that the attractiveness of the effective field theory is getting somewhat diminished. You don't really have to, follow field theories to get the full, whatever is reliable. Okay. So yes, effective field theories are good, but you must avoid the trap of trying to make them look more and more like fundamental theories, which they are not. So they are supposed to work in some limited domains, and your formalism should keep that in mind.
Any other question?
I'm almost sure I won't hear it, so maybe you want to come here and tell me? Yeah. I'm sorry.
No. Sir,
Yeah.
initially you stated that the Einstein's work was criticized by some other general physicist, but why were their work was accepted as...
Why should?
Why were their work accepted when they criticized Einstein's work? Yeah, Rosenblum's and other works.
Can somebody talk slowly? Yeah.
Sir, you stated that at first Rosenblum's work criticized Einstein's work, but we know that Einstein's works was appropriately correct. But why was Rosenblum's work appreciated or even accepted to a certain extent?
Rosenblum's work was very complicated because he went up to, third order post-Newtonian approximation, and he obviously has made errors in this. And basically what all these guys tried to do was take into account the back reaction, the gravitational radiation reaction, and that even in electromagnetism is very complicated. And if you're not careful, you get nonsensical results like runaway solutions, causality violation, and so on. So, short answer is there were calculational errors in those things. It turns out that in the leading approximation, the radiation reaction does not alter the source of gravitational radiation. Or the one graviton transition operator that I talked about is insensitive to radiation. But that's only at the leading order. So if you go to fifth order post-Newtonian, then this radiation reaction becomes important, and that's why calculations also become quite intractable. I hope I answered your question.
Yes, sir. Thank you, sir.
Any other questions? Not, I had a question. So Kip Thorne had this formulation of GR as a nonlinear theory on flat space. Are you aware of that?
Which one?
Kip Thorne had this formulation of GR
Yeah.
as a nonlinear field theory in Minkowski background, so that physics would emerge easy.
Who is this person?
Kip Thorne.
No.
Okay.
I don't know. Maybe if you point out some reference.
I will. I was curious to know if there was something. Okay, if there are no further questions, it's my great pleasure to, give Professor Haridas this memento of our appreciation. This is a pictorial biography of P.V. Raman.
Thank you so much.
Okay.
I shall
Welcome. Yeah.
greatly treasure this
Yeah.
and my visit, and thank you for everything.
Thank you. Thank you for coming. Thanks, everyone. And I'm not even sure.